Students, we've got 3.5 weeks left to go, and we are moving on from electric fields into talking about current electricity, and we're going to be focusing specifically on DC, or direct current electric circuits. Now, this is something that hopefully you touched on way back in junior high. I'm not sure if it was 5th grade or 6th grade or 8th grade is the last time you saw this, unless you've had it in IPC, but we're going to be playing around with some circuits. We're going to be looking at both real world and simulated examples of both. So I'm going to start this off just by covering a couple bases. My internet connection is unstable. That's always good news. Love to hear that. We're going to be taking a look at circuit diagrams to start off with, talking about, what makes a circuit a usable circuit and what is an open circuit versus a closed one. We're going to be talking about potential difference or voltage and looking at a little bit of the math involved with that. Now, when we talk about circuits, one of the things that we're going to be looking at and doing is we're going to be making and drawing schematic diagrams, which are basically kind of a shorthand that symbolizes different components in an electrical circuit. I've got a separate handout in that big packet of stuff posted that has a list of some of these you're going to need to know, but a few of the symbols are located on here. Pretty much if you've got a line, that's going to be a wire of some kind. If you've got something that is acting as a resistor, and we'll talk about what a resistor is here in just a minute, it's going to be kind of a spiky wave in the middle of the line. If you've got a battery or a dry cell, then it's going to be a long and short line kind of breaking up the wire. A switch looks like this down here. It could be either open or closed. And then in some cases, we're also going to be having lamps. And there are different ways to symbolize a lamp or a light. There's these two here. I've also seen it done as a circle with an X in the middle of it. But between this and between the other handout I've given you, that shouldn't be hard to figure out what it is you're looking at when you're looking at a schematic. Okay. An electric circuit, the reason they call it a circuit, it comes from the same word that we get circle from, meaning it has to be a closed loop in order for it to work. Because in order to have electric current, you've got electrons that are flowing from atom to atom in a bunch of neighboring atoms. In order for that to happen, there has to be a circular path for them to travel. You have to have a complete closed circuit in order for that to work. If there's a break in that circle, then electrons will not flow, and you do not have electrical current. Okay, like I just said, closed circuit provides a complete path, an open circuit. And you can see this when you play with a light switch. When you flip a light switch on, what you're actually doing is you're closing the circuit, which allows electricity to flow into and through that light bulb, and then some of that electrical energy is changed into light and also heat. When you flip the light switch off, you open that circuit, you break that circuit, and the electrons don't flow. So case in point, what we've got right here is and this is kind of funny because I've been doing a lot of amateur electrician stuff around the house over the break because my wife wants to kill me. And what we've got when we wire up something like a light fixture, you'll typically have two wires that's attached to. Typically a black one, which is the hot side. That's going to be where you're going to have electricity in. And then you've got the white side, which is the neutral side. And what happens in a light bulb, for example, here, is that electrons are going to flow from wherever you've got your switch into the bottom pole of this light bulb. That's going to follow a lead that takes it up through the light filament. In old school light bulbs, this was made of tungsten because tungsten can get really, really hot without melting, and it can give off lots of light. Then after the electrons flow through there and they're slowed down by the resistance of that, they'll flow out the other side, which is wired up to the jacket of the light bulb, and then it's picked up by this other side, and then it will go back to the switch and then make a return path. So it is a constant circuit in order to get a light bulb to light up. Now we're going to look at a little bit of the math, and we're going to talk about some of the different types of circuit. Before we do that, I'm going to give you a couple important things to write down. Okay. First of all, we're going to make a magic triangle. In that magic triangle, up at the top, we're going to have letter V. And then on the bottom part, we're going to have the letters I and R. Okay. The letter V has to do with voltage, or something that is also called potential difference. The I stands for current, and the R stands for resistance. Voltage, the unit for voltage, that one's easy. It's in volts. Current is in amps. And resistance, we get another fun Greek letter here. That's the Greek letter omega, and we shorten that to say ohms. Okay? The other thing I'd like you to write down while you're here is I would like you to write down this nifty mnemonic device. PVC is SIC. PVC is sick. And I'll explain what that means when we come to it, but that's going to be really handy to remember, PVC and SIC. Let's jump back over to our slides here. So two different types of, well, the two main types of circuits that we're going to be examining are called series circuits and parallel circuits. A series circuit is one where you've got several components within a single circuit, within a single circular loop or pathway, and they're all in line with each other. When we think about a series on TV, we think about episode 1, episode 2, episode 3, episode 4. They come one after another, and the same kind of thing in a series circuit. When you've got a series circuit, at every resistor in that circuit, the current is going to be the same. Okay? And this is where that SIC comes into place, because what we say for SIC, what that means is that in series, current is constant. Why not SCC? Well, because we remember that current is symbolized with the letter I, and it just makes for a better mnemonic device to say SIC instead of SCC, because that doesn't really mean anything. So in series circuits, current is constant at every point in that circuit. You'll see what I mean when we look at some examples. And so when we find, if we know the resistance value for all of the resistors that are in a series circuit, we can add those together to get the total resistance for the entire circuit. Okay, and that's something called equivalent resistance. And it's easy enough in a series circuit. Equivalent resistance is just the sum of all of the resistors in that circuit. In other words, go back. Total resistance or equivalent resistance is equal to resistor 1 plus resistor 2 plus resistor 3 and so on for however many resistors you have. What we've got right here in this slide are, well, we've got a very, very simple series. You have a power source, okay, in this case it's a 9-volt battery, and you have a circular pathway through which those electrons are free to flow, okay? They flow from the, now this is going to be where I screw things up. I believe they flow from the negative end to the positive end, but I could have that backwards. It's really not that important for what we're talking about here. But you see what they're doing is they're flowing through this first lamp, which is our first resistor, then to this second lamp, which is our second resistor, and then on back to the power source, which is our battery. You can see this in the schematic diagram here. You've got our battery symbolized as those two lines, resistor number 1, resistor number 2. Now, since current is constant through this entire thing, maybe it would help for me to sort of explain what current actually means. In this context right here, current and a good way to think about it is kind of like the current that you would have in a body of water, okay? It is movement, okay? So if we're talking about current, this would be the speed that electrons flow. And so if we talk about something having high current, it means the electrons are flowing very, very quickly. It doesn't have anything necessarily to do with how many electrons are flowing. That has to do more with voltage, okay? Good way to think about voltage would be, okay, so if I am getting hit with water from a water gun and I'm getting hit with water from a fire hose, and they're both moving at the same speed, which one is actually carrying quite a bit more oomph, quite a bit more power behind it? And that would be the fire hose. The reason is because there's a larger amount that is moving at any given speed. So voltage would be more akin to the amount of electrons flowing. Now, the reason why current is constant in a series circuit, let me jump back over to that. If you look here, any electrons that are flowing in this path have to flow through both of these, which means that the speed that they're flowing is dictated by both of these resistors, both of these lamps that are slowing them down as they pass through there. And so the speed that they're passing through this entire circuit has to do with everything that's resisting that speed. So what I could do to calculate the current or to calculate the speed that they're flowing here is I could read the volts off the side of the 9-volt battery, and it's probably going to be pretty close to 9 because it's a 9-volt battery. I could add up the resistors in ohms from both of these, and then using my formula, or using my magic pyramid right here, to calculate current, I could take voltage divided by my total resistance, so 9 divided by whatever my resistors add up to, and that would give me the current. I believe that there's a sample problem coming up. Oh, now this will come more into play when we look at complex circuits, but what we've got right here, it's saying that if you've got multiple resistors on a single loop, you can treat them as a single equivalent resistor. So let's say that this one had a resistance of 3 ohms, and this one had a resistance of 2 ohms. Well, the total resistance on that particular branch would be as if you had a single 5 ohm resistor. You're just adding them together. So let's see here. All right, well, let's do this one. 9-volt battery is connected to 4 light bulbs. Find the equivalent resistance and then the current in the circuit. So what we're going to do is we're going to take a look at this, and the first thing we need to do, we need to remember that in series, current is constant, SIC. So we know that the current is going to be the same no matter where we look for it on the circuit. So we're going to add up all of our resistors, 2 plus 4 plus 5 plus 7. 2 and 4 make 6. 6 and 5 is 11. 11 plus 7 is 18. So we have a total resistance of 18 ohms. Okay? If our total resistance is 18 ohms, we know that we are dealing with a 9-volt battery. We want to find current. Yes, this is simple math, but we have to walk. Well, I'm sorry, we have to crawl before we can walk. We have to walk before we can fly. And so given voltage equals current times resistance, and current is voltage divided by resistance, what I'm going to do is I'm going to do I equals V over R, which means 9 divided by 18, which means that our answer is going to be 0.5 amps, or 1/2 of an amp, meaning the total amount of electrons that are getting through there. I'm sorry, no, the speed that we're getting through. Why am I doing amps? Oh, because it is amps, okay? Amps or amperes, that has to do with the speed of that flow. So now, is that a big number or a small number? I don't know. It's not going to be enough to kill you, if you touch your tongue to it or something. Don't touch your tongue to things. That's weird. So they're going to do what we basically just did right there. Resistors. Oh, this is nice. There's our circuit diagram, our schematic of the picture that they just had. They add up and get the total resistance, which is 18, and then like we just did right there, 9 divided by 18 gives us 0.5 amps. Okay, I'm not worried so much about power. I don't know that we're going to really talk about power. Power is easy to calculate. Power is just voltage squared divided by resistance. And so in this case, 9 squared divided by 18 gives us 4.5 watts. But I'm okay with us not getting into power if you guys are. So we're going to move on here. Now, here's the thing about series circuits, and the advantage of it is that they're very simple to draw and they're very simple to make calculations of equivalent resistance. The bad thing is that if one part of that circuit goes out, let's say that you have a bulb break, then that breaks your circuit, and that means that no electrons can move, or in other words, you're not going to get any of these lights lit up. This is what happens with cheap Christmas tree lights, like the kind that I usually end up buying. When one bulb goes out, it burns out or makes several other bulbs go off that are in that strand. So you can't have any current if you don't have a complete circular path. Now, this enters next thing we're going to talk about, which is parallel circuits. Now here you've got a schematic of a parallel circuit. And what you have in parallel is you've got multiple parts that are wired up on separate paths. So if you take a look at this schematic right here, what we actually have are several circular paths through which the electrons can move. There's one path that goes through this first bulb and comes back. There's one that goes through the second bulb and comes back, and so on. So each one of these bulbs is on its own circuit. If one of these bulbs was to burn out, let's say that this one right here completely burned out, then all of the other bulbs will stay lit because they still have a complete pathway for those electrons to flow. Okay. Most of the lighting in your house is probably wired in parallel. And I know this because when a light bulb goes out in the ceiling, it probably doesn't stop all of your plugs or other lights in your house from going out. That would be a real pain. What we've got right here is we've got a parallel circuit, again, using 2 lamps and wire and the same 9-volt battery. You've got one pathway here, the other goes through here, and you can see in the schematic here, they are wired up in parallel to each other. Now that does change the math up a little bit. For one, the current does not stay constant in a parallel circuit. Current in a parallel circuit is actually the addition of the currents at each resistor throughout that circuit. However, voltage does stay the same through a parallel circuit, which brings us back to the other part of the mnemonic device here, PVC. PVC stands for, I'll put it down here. You're already way ahead of me. In parallel, voltage is constant. Okay, PVC. And so when we're doing math and looking at parallel circuits, we know that the voltage or the potential difference or the amount of electrons moving through there is going to be the same at every resistor that's in that circuit. So let's come back to our slide here. So when you're calculating resistance in a parallel circuit, it's a little bit different. Instead of saying that your total resistance equals R1 plus R2 plus R3, it's actually the inverse of each. And it's 1 over the total resistance is equal to 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. And this is a classic place where physics students forget that they know how to do math and mess this up. So that's going to be a handy thing to jot down somewhere. The total current is equal to I1 plus I2 plus I3 plus I4 for every place on the circuit, but the resistance is calculated a little bit differently. I'm going to see if we've got a practice problem for this one too. Okay, yeah, and it tells you how to get equivalent resistance right there. You add up the reciprocals of all your resistors. Okay, here's a practice problem for us. I have a 9-volt battery wired up to 4 resistors. We want to find the equivalent resistance for the circuit and the total current in the circuit. Okay, so let's start off by looking at a schematic diagram here, if they'll give us one. Okay, that's nice. Okay, so what we've got right here is we've got 4 different resistors with resistances of 2, 4, 5, and 7. I'm going to come out to my paper. And we're going to take a look at this. If we know R1, R2, R3, and R4 are 2 ohms, 4 ohms, 5 ohms, and 7 ohms. Okay, it doesn't really matter what order we look at these. If I want to find total resistance here, then 1 over my total resistance is going to equal 1/2 plus 1/4 plus 1/5 plus 1/7. Okay, let me get my calculator out here. And if you've got fractions on your calculator, great. I prefer to work with decimals. And so what I do when I put this in is I probably just do 1 divided by 2 plus 1 divided by 4 plus 1 divided by 5 plus 1 divided by 7. And it's going to give me 1 over my answer. So that's going to be the way that I'm going to work it here. So I'm going to do 1 divided by 2 plus 1 divided by 4 plus 1 divided by 5 plus 1 divided by 7. That gives me 1.09 and such. Now I need to flip that over, so I'm going to do 1 divided by answer. That's going to tell me that I have a total resistance of 0.915 ohms. So my R total equals 0.915 and change ohms. Okay, we know that let's jump back over here, make sure I'm not missing anything important. Okay, so we now know our equivalent resistance. We need to find our current. Well, we know that in parallel our voltage is going to be constant, so it's going to be 9 volts at every point in there. So we should be able to then do I equals V divided by R, which means for the overall current of the thing, we should be able to do 9 divided by 0.915, which is going to get us awfully close to 10 if I'm not mistaken. So let's do 9 divided by answer. I get 9.84, so I'm going to say 9.84 amps, or 9.84A. Now, the important thing to keep in mind, going back to our circuit diagram, is that at every point on this diagram with each one of these resistors, you're actually going to have electrons moving at different speeds. And so it's going to be moving at a different speed through this branch than it is through this one, or this one, or this one. Generally speaking, when you've got lower resistance, you're going to have higher current because the resistors are not slowing the electrons down as much. So if I look at these 4 branches, the place where the electrons are moving the fastest is going to be up here through this 2 ohm resistor, and the slowest is going to be down here through this 7 ohm resistor. And we can actually calculate at any one of these what the current is going to be doing. So I'm going to do that real quick just to kind of show you what I'm talking about. So if V equals I times R and we want to find current, that's going to be volts divided by resistance. And so at our first one, we're going to have we're going to have 9 divided by 2. At our second one, we're going to have 4 divided by 2. 9 divided by 4. Lies. At our third, we're going to have 9 divided by 5. And at our fourth one, we're going to have 9 divided by 7. Okay? So I could find the current at each one of these. Okay, 9 divided by 2, for sake of argument, that's going to be 4.5 amps. 9 divided by 4 is going to be 2.25 amps. I made myself some paths here. 9 divided by 5 is 1.8. And then 9 divided by 7 is 1.29 and change. Now, I wonder what happens when I add all of these up. Let's look. So I go 4.5 plus 2.25 plus 1.8 plus 1.29. I get 9.84 as the total current. Now take a look right here. We got 9.84 just a minute ago by taking our total resistance using this formula right here to find it. So either way, you can math your way around a parallel circuit. Now let's jump back over and see where they take us here. Okay, so we have figured out our total equivalent resistance like they did here. Total current is going to be voltage divided total resistance. So we get, now how did they get 1.09? What did I do wrong? Oh, it's 1 over 1.09. Ha, kidding. I knew that. So it's still 0.917. We got 0.915, but same thing. So 9.8 amps, that's what we got when we worked it. So far so good. This is a handy dandy table to maybe even print out a copy of when you're looking at series circuits versus parallel circuits. The current in a series circuit is constant because remember SIC. The voltage in a parallel circuit is constant, remember PVC. And then again, here's how we find equivalent resistance in either series or in parallel. And then to find the other thing that you're missing, total voltage in series, you just add up the voltage at each resistance. And then current in parallel, you add up the current at each resistor, and that gives you the total of that. That should at least get you started on some of those calculations. I'm going to be filming tomorrow morning and working some of the resistance problems in that first assignment of yours. So be sure and tune in and take a look at that. That'll be Tuesday morning at 10 o'clock, and I'll post a video right after that. At this time, I am going to ask if anybody out there, and there's only one of you right now, if any of you out there have any questions. So I'm going to unmute you. Do you have any questions? Okay. I think, is that the last slide? I think that's all there was. Nope. There's a bit more because it does talk about complex circuits, but I think we're going to maybe wait and go over that before we go over the some of the other circuit shenanigans tomorrow. So I'm just going to save that, and I'm going to go ahead and call this done. So everybody watching this, tune in later to get some help with that. But in the meantime, go take a look at some of those resistance problems and see what you can figure out on your own. Have a great day.